Everyone, welcome indeed to the fourth week of the seminar series. The title for today is Starting Simple 2. Last week we looked at hands-on methods for water quality monitoring, and today we will look at starting simple hands-on methods for water quantity monitoring. And just as Julia said, here's the schedule: 4 more weeks coming up with other great presentations. For today, we have two great speakers, and we're very happy that they're with us. The first speaker for today is Björn Weser. He comes to us from the University in Gießen in Germany. He has a background in environmental management and engineering, and he conducts research in tropical catchments with a focus on hydrogeochemical modeling, combining groundwater measurements with other measurements. He leads the junior research group HYDROCROWD and manages the Excellence Center SDG Nexus, a global community of universities, research centers, and stakeholders promoting the achievement of SDGs. And the title of his talk is Citizen Science in Hydrology, Participatory Water Management in the Global South. Björn, very much thank you for being with us. We look forward to your talk. And everyone, as Julia said, please ask questions in the Q&A, and we'll go to them after the end of our second talk.
Thank you. I'll just quickly share my screen. You should be able to see it now, yeah?
Perfect.
Okay, great. Okay, yeah, thank you, Ilja, for the kind introduction, and a warm welcome also from my side to everyone who joins the two-day session. And before we start, I also want to take short this opportunity to say that I really enjoyed this seminar series, which I followed on YouTube the last weeks. And I think we really got all very valuable input related to different aspects of citizen science. So thank you for this initiative and also for the invitation to be part of the series today. And yeah, today I'm pleased to talk about citizen science approaches for water quantity monitoring. And in this presentation, we will explore a bit about why citizen science is a valuable tool in hydrology and discuss its application in the case study in Kenya we did. And I will also talk a bit about the challenges and opportunities associated with citizen science. And also finally, I will showcase a little bit the new research project Ilja just mentioned, the HYDROCROWD project that investigates crowdsourcing approaches in 3 countries in the global south. So yeah, join me as we dive a bit into the world of citizen science for water monitoring, where like ordinary citizens can do some extraordinary contribution to science. And whenever I give presentations related to this topic, I really like to start with an animation I actually made for my PhD defense a couple of years ago. And on this map, you can see discharge data, which is available from the Global Runoff Data Center at specific time steps. And what you can clearly see and identify is that the number of stations on the data has reduced actually dramatically in the last 30 years. And this is particularly true in the global south, since there are not enough resources to operate extensive monitoring networks. And hence the number in these regions really decreased. You can clearly see it here in Africa, for example, where almost all African stations disappear, but also very highly in Latin America. And yet, of course, these are the stations which are actually extremely affected by extreme weather conditions and climate change. And this is something we should keep in mind when we talk about this topic under data reduction. And as we all know, hydrological monitoring is important to manage water resources effectively and sustainably. And without this data and a sufficient amount of data, this decision-making becomes really difficult and water management will be actually less effective. These issues are, of course, not new to the hydrological society, and they have been actually described in 2006 quite vividly in EOS. I really like this picture where global water data was described as an endangered species. And in the recent years, volunteers have become increasingly involved in gathering knowledge, such as water levels, for example, and this is often referred to as crowdsourcing or participatory monitoring. And by involving more actors, activities that would otherwise be too difficult or complex or expensive can actually be conducted. And this is, again, very relevant for countries of the global south, where often these resources are not available to operate such complex monitoring networks. And when sampling hydrological data with volunteers, often questions related to the accuracy, temporal resolution, or something like this arise. And also, actually, very little is known about why people choose to devote their time to such kind of projects. And in the next few minutes, I will share a little bit from what we learned from a project we launched in Kenya in 2016, and also what we are going to do in the next years to address these issues a bit more. So how did actually the setup look like in Kenya? So in the first project phase, we installed 13 water level gauges at frequently visited sites in Kenya. And next to some, we placed some simple signboard with instructions about the project and the water level gauges so that everyone who passes by the station was able to participate in the project. And for the data submission, we developed a low-cost data processing server, which was based on a Raspberry Pi and these USB dongles here. And the system had the benefit that it lowers the barrier of participation because citizens didn't require any internet connection or they don't need a smartphone to submit data. And that's something which was back in 2016 actually quite an issue in Kenya, where just 30% had a smartphone more or less. And furthermore, it had the benefit that the system had a direct link to the citizens, so we were able to generate response messages, which were sent back to the participants actually immediately after they submitted data. And these messages could either be something like thank you for your participation, which motivates people, or also include some indication of errors. For example, if the station ID was missing, or if the reported water level was higher than actually the scale of the gauge. And then people were able to correct their measurements directly. And the entire system is actually quite cheap. It was around $100 US. So it's also, the idea was to have it affordable for low income countries. And it was also able to operate on a simple power bank here. For $20 more or less, so that it was not affected by power cuts, which actually also frequently happened. And all this data was then available in real time on the web interface. And yeah, it turned out to work quite reliable. And after the first phase worked well, we initiated a second project phase a bit later, where we also tried to include some water quality monitoring, which was done together with some selected volunteers. They were selected because in this case, they needed some special equipment. So we equipped them with nitrogen test strips or turbidity tubes, which they then used to measure the water quality parameters. And then they transmitted the data using the same system with the text messages. Yeah, so that we're able to see the data and also share it with them later online. What we actually observed in Kenya was that there was a high participation. We had in the first project phase around 4,000 observations, and only 300 more or less out of them were flagged as invalid. And this was mostly caused because the system was kind of mishandled. So people were applying for a job or advertising something, or they simply missed, for example, to include the station ID. So it was not possible to link the measurement to one of the stations. And many people actually only submitted data once. This is quite interesting. We had like 260 participants and around 50% of them only submitted data once. But if you look where the data actually comes from, then you see that they are coming from so-called, or we call them highly active individuals. So there are people which had more than 10 measurements, and these people actually contributed to more than 80% of the overall data. So it's really important actually to keep some people or the people motivated and let them be connected to the project. Regarding the data quality, we actually saw very excellent agreement between the crowdsourced data and source of a radar sensor, which we installed at one station or like a little bit upstream of one station to have some reference. That's what you can see here on the graphic. So we have this blue line as a radar data and the blue dots as citizen science collected data. You see we have a very good agreement, but also if you look at the plot itself, you see that the peaks are well covered as well as the base flows are actually very well covered as well. And this actually indicates a bit that these easy to measure parameters like water levels can actually be recorded by volunteers quite well, even without a special training, because we didn't provide extra training. So the system was open. Everyone who passed by was able to participate. We did some training with some of the communities, but overall it was an open system, and yeah, it works also well without training. Of course, I mean, if we talk about citizen science, then it's clear that citizen science projects really rely on the participation of volunteers who contribute their time, effort, and expertise to collect some of this data. And of course, we also see that sometimes volunteers may stop participating. And what you see here on this graphic, for example, is the aggregated monthly data points per station. And you see it's quite diverse even within the catchment. So we have stations which are actively all over the first project phase. Then we have stations which were actually not active in the beginning, but we might have like 1 or 2 individuals which were certainly very interested in the approach, and they then started to contribute data very frequently. But we also have stations which were active in the beginning, and then later on they were actually not transmitting any data anymore. And we also tried to assess a bit the reasons behind this. And what we saw is, of course, our project is actually located in a rural area in Kenya, and we observed that a certain amount of participants leave the area. They move to bigger cities like Nairobi to, for example, obtain a job. Also, other participants mentioned that they encountered difficulties to access the stations, or that the stations were damaged. It's the case in this station that was simply not available anymore because it was flushed away. And this shows that a certain amount of maintenance is required, of course, whenever some physical equipment is involved. And this might be, for example, a bit different, like in the Crowdwater project, where like virtual staff gauges are used. So it's no risk that the station is damaged in this case. No? And some of the participants also raised some concerns regarding the costs related to the text message, because the text message system we used, the people needed to pay like one shilling, which is probably 1 US cent for the transmission of the data. We made experiments with some stations where we paid back this money automatically, and then indeed also the data contribution increased quite a bit. And communication and data sharing is definitely an important aspect. So if participants feel that they are not being adequately informed or involved about the project, they become disengaged and stop participating. And for this reason, for example, we organized meetings with participants or stakeholders, or also use the text message system to keep in contact with our participants. And it's also what you see here. So we really just printed this plot with the data the citizens generated. We brought it to the community and we showed them what they're really doing, because not all of them also have access to internet or can easily plot this data, and they basically collect it. And this is really some quite important part we also realized. The main findings of this case study in Kenya is summarized here, and I can't go much into detail because of the time constraints, but I really invite you to just maybe explore a bit more the results in the publications listed here if you're interested, or also later in the discussion, of course. And furthermore, I would also like to draw your attention to another presentation in the seminar series. So Lutz Breuer here from University of Gießen will present the results related to the rainfall runoff modeling study in Kenya on 19th of April. There we were able to show that the citizen science data is actually very useful also to use for hydrological modeling if it's combined with some water balance generated by satellite data. And overall, we actually learned quite a bit in the project in Kenya, but the question is also if this actually also applies to different parts of the world. And this was a bit one of the things we had in mind when we created the HYDROCROWD project. And this is something we hopefully can contribute with more in the next years. And I will use the final 1.5 minutes to shortly go over the project. So we have 3 main objectives actually in HYDROCROWD. First of all, we try to assess the feasibility of participatory monitoring approaches in different study areas outside Kenya. So we work in Tanzania, Ecuador, and Honduras. And the reason why we choose the setup is that we try to integrate also different target groups. So in Tanzania, we will work with international tourists which climbed Mount Kilimanjaro. In Ecuador, we usually work together with local tourists in the national park, and in Honduras, we work closely with local communities and farmers. And we also use some surveys to analyze the data submission behavior and the motivation and behind these different groups. And we will also have a closer look into modeling approaches using some remote sensing data or also some artificial intelligence to do some data gap filling, for example. This is very roughly the approach we're using. We're going to also collect some weather data this time, especially rainfall will be interesting because it of course also serves as an input for the modeling, In Kenya, we use automatic stations. Here we'll use a mix, so we can also test how the uncertainty in the precipitation measurements of citizens play a role. And we will use an app this time. Spotter on here is actually a screenshot of the Crowdwater app from Zurich. We go the same way this time because it allows us also to verify the location, the time, and of course also some pictures which can be transmitted. So we will see how this is going. And also the water quality monitoring, the turbidity tubes in this case will be really mounted close to the river, so citizens can go there, do the measurement, and then directly transmit the data. Yeah, since I can actually come to an end, I mean, this is our team. We're very happy to start now since January. We are complete, Susanne and me leading the group, and we have our 3 PhD students, Fabian, and Jasmin. And yeah, we are looking forward to see what is coming there. So thank you very much. I'm slightly over the time, I think. And I think in general, citizen science is really, for me, exciting and promising field that has some potential to improve a bit data availability if it's done correctly, and also if the community is really included in the project. And yeah, I hope maybe it inspires you a little bit also to use citizen science maybe in your research, and I'm very happy to answer any questions later in the discussion. Thanks, and I will stop here because it's 40 minutes or something.
Thanks a lot, Björn.
Let me just stop the screen share. Yeah.
Would be great. We will have the question and answer session for your talk together with one for our next speaker later. For people who are now really looking at the background behind you, very nice to see a big poster of the Sustainable Development Goals there as well. Our second speaker for today is Katie Bradford. She is at the University of Wisconsin, so in the US. She's a program manager for the Water Action Volunteers Citizen Science Stream Monitoring Program. As a program manager, she recruits and trains volunteers all across Wisconsin to collect high quality data on their local waterways. She collaborates closely with the Wisconsin Department of Natural Resources, extension staff, and partner organizations to identify water quality monitoring needs. And she also looks at expanding water science education and stewardship to Wisconsin residents of all ages. Katie, we're very much looking forward to your talk. Thank you for being here.
Thank you. I'm going to go ahead and share my screen. All right, how does that look?
Perfect.
Awesome. Okay, really happy to be here today. My name's Katie Bradford. I am in the state of Wisconsin. Let's see here, just a sec. There we go. In the state of Wisconsin in the US, and I run our volunteer stream monitoring program. So we started WAVE, Water Action Volunteers, in 1996. So we've been doing this for about 25 years, 26 years. And in Wisconsin, we have 45,000 miles of wadable streams. So our volunteers are only monitoring streams that they can wade across, walk across. So we have 537 unique stream sites that our volunteers are monitoring. That was as of last year. And so we have over 500 volunteers in our program, and the map on the left is showing stream monitoring sites across our state. All the dots are stream monitoring sites from 2021. So our stream flow monitoring that we do is in 2 different areas. So all our volunteers get started as baseline monitoring volunteers. So they are getting a baseline reading of the stream, kind of almost like a screening of the stream. And they go out once a month from May to October with a teammate, and they are collecting data on the water temperature, water clarity, dissolved oxygen, in addition to stream flow. And so that's a single point in time rather than a continuous stream flow measurement. And then we also have volunteers who have more experience going out and collecting water samples to test for nutrients in the stream, like total phosphorus or nitrogen. And sometimes they are also doing a stream flow discharge measurement so that we can better understand the pollutants discharging through our streams. So to train our volunteers on this method, we start them off with a short online course so they can spend some time on their own learning, kind of self-studying our methods. And that takes about 1 to 2 hours. You can check it out yourself. It's publicly available on our website and it's free. And then we have them sign up for field training, which takes about 3 to 4 hours to go through all those baseline methods, including stream flow. So that's what you're seeing in the picture on the left is our volunteers are practicing stream flow at a field training. We give them a free stream monitoring equipment kit and an informational packet. So they have the methods and the data sheets they need to go out in the field during the growing season. And then we have volunteers enter their own data into our state database. So that's the same database that like biologists, professional biologists are using to submit data, and the volunteer data is combined with that. So I want to share with you the method that we teach volunteers. We do the float method. So when we're at trainings, I find it valuable to teach the volunteers the equation that we're using so they understand the different components that add up to getting that stream flow discharge reading that they're going to get, because this is definitely the most tricky parameter that we teach, and it does confuse people. So it takes a little extra time. It takes like an hour to teach it. So our units are in cubic feet per second. So we start part 1, we teach them, you know, you're going to go out to your stream site, you're going to cut the stream like a cake, and you're going to measure its width, and then you're going to get an average depth, and that's our area. And then the second part that we're going to do is we're going to measure the velocity of the water. So to do that, this is where the float test comes in. We have to determine how many seconds it takes a tennis ball to float 20 feet down the length of our stream. So that distance is the 20 feet, time is how long it takes. And then I'll mention that we have a correction factor too. So because this is a little complicated, I always start at our trainings drawing out what this looks like, writing out the equation. They can ask questions and start to get a handle on what it is. And then we go out in the stream with the equipment. So one reason we use this method versus some kind of meter is it's a lot more affordable for the equipment. Actually, the net, what we use is an aquatic D net, which we also use to collect macroinvertebrates in the stream, but we mark the depths on the handle. It would be even cheaper to use a measuring stick instead of the net. The net's the most expensive part, actually, but they're already using it for something else. So we have a measuring tape, wire flags to mark sections and lengths. We use a simple tennis ball and we cut a slit in the top of it, and I'll explain why in a sec. Then we provide a calculator, a stopwatch, which for those who have phones and are comfortable taking them in the water, they can use those, and then also stakes. And one thing many of you may not have to deal with is that since you're in the metric system, since we use cubic feet per second in our stream flow discharge, we have to instruct people to think in decimal feet or tenths of feet, whereas most Americans are used to thinking in feet and inches, but those are 2 different units of measurement. So we have to, this is kind of a source of error that pops up, and we have to constantly remind volunteers, you know, your tape measure is in decimal feet, and we give the example here, 8 3/8 inches. You convert that, and that's converted into 0.7 feet. It's a lot simpler, in fact. So we have them choose their section of stream we'll be monitoring. We have them do a straight section of stream, so no meandering, no pooling, that's water is flowing normally. And that's where we're going to mark it with the flag where we're going to do our measurement. So that part 1 is we're cutting the stream like a cake, and we are starting off by measuring the area of that section. So we do width first. So we stretch or tape measure across the stream, and we measure from wetted edge to wetted edge of our stream. So, you know, the 0 point is where the water starts on the bank on one side, you're going to walk to the other, and where the water ends, that's your width on the other side. And you can use stakes, we tell them, to clamp your measuring tape taut across the stream, because then we're going to use that for calculating our average depth. So part 2 of the area is calculating an average depth. And what we do is we use up to 20 depth points to get an average depth of the water. So we generally have them take a depth measurement every foot. It's really important that they're measuring at equal intervals across the stream, and they take a depth measurement at every foot. And this is in a picture of a couple of our volunteer teams learning how to do that. They're heading across the stream. You can see them using the tape measure to make sure they're, you know, equally spacing their intervals, and then they look at the water depth with the net. And this is what our data sheet looks like. So we have them take this into the field. Kind of in the bottom left there, we have the 20 possible depth points. And so I always have to give the example, you know, if we have an 11.5 foot wide stream and we're measuring every foot, we're going to end up with, you know, 11 points, the first point being 0, which is representing both banks. So on the data sheet here, we have 12 points. And we have to emphasize, you know, some errors we see. People add extra zeros at the end to fill in the rest of the points, which would throw off our average depth. So we have to be really careful about that. But generally, volunteers don't have to do any calculations or math. They just write the depths, they write the width, they write the velocity, and our database auto calculates the discharge for them. And then if the stream is more than 20 feet wide, it gets a little more complicated, but we still have them take that depth, divide it by 20 points, and then round up to make it a little easier so that they're still taking depth measurements at equal intervals. So if their stream is, you know, over 20 feet, 23.5 feet wide, then they would likely record depth every 1.5 feet. And then part 2 is taking the velocity. So this one's a lot simpler. The hardest part is done. They mark a 20-foot length of the stream with where they measured the area, that cross section in the middle at the 10-foot mark. And then we have them fill that tennis ball that I mentioned earlier. It has a slit in the top. That's so they can fill it partway with water, because it's going to float on the surface, but we don't want it to be blown by the wind or anything. So it kind of sits in the water a little bit without sinking. And then they're going to see how long it takes the tennis ball to float that 20 feet. They do it 4 times. They use their stopwatch, and they'll do it on one side of the stream and the other down the middle, so they get a nice velocity, average velocity. And then the last piece of this is the correction factor. So because the ball is floating on the surface and water flows differently, you know, on the bottom and middle of the stream compared to the surface, we have this correction factor on our data sheet. It's just rough or smooth, simple as that. And that's part of the equation. And so if the bottom of the stream is rough, so it has lots of boulders and rocks and pebbles or lots of vegetation and plants, then they'll circle the rough correction factor, because the water is encountering more resistance on the bottom and it's slowing the water down relative to the surface. And if it's a smooth bottom stream, like smooth sand or bedrock, then they select the smooth correction factor. And I just have a few more points to share. One is that this is a really common method to use, at least in the US, but it does overestimate the stream flow by about 24% because we're averaging a lot of things. And so when our volunteers enter their points into our database, the database auto corrects for that. It multiplies their value by, I think it's 0.76 in order to bring their stream flow discharge down to what it is. And if we compare this with a local stream gauge set up by the US Geological Survey, it's right on, which is pretty cool.
2 minutes.
So thank you. So we tell volunteers, you know, if you have a stream gauge near your stream site and you're doing the stream flow float method, that we teach, compare it to the stream gauge, make sure you're correcting for that 24%. And then sometimes it can be helpful, like I said, to have volunteers do the math themselves to learn. So we do have this worksheet, which we provide in the trainings, and it looks pretty complicated here. So we do guide volunteers through it, but this really helps them understand how all these numbers come together to get a stream flow discharge, and they seem to get it no problem once they've gone through it. So this can be really helpful to understand the concept. Yeah, so that's all I have. We do share our stream flow and all the other data on our website on our Shiny dashboard. And our stream flow data is, like I said, kind of point-based, one point in time. So generally they're not out there right after a storm, so they're not getting those peaks. They're just getting kind of the bottom, the baseline flow. And that is the intent of what we're going for. So that's all I got for now.
Thank you, Katie. Very interesting. Thank you for the people who have already written a couple of questions. We will start with them now. We start with some more technical questions in the Q&A. Maybe we start with Björn, since that's the first question in the top, about the turbidity meters or the portable turbidity tubes that you have. Maybe can you say a little bit more and how you calibrated them?
Yeah, sure. I mean, the nice thing is I can saw the questions while the talk was ongoing, so I brought one. We are using this kind of vague text tube, so they're actually commercially available. Unfortunately, in Europe, we had to import them from the UK, but basically they have just an indication, you can see it there, most likely not. And what's happening is kind of there's a very small mark inside. So you look from the top and then you start filling up the water and this mark disappears at a certain level. And this level is written on the tube on the side. So then this is calibrated for checks and turbidity units, basically. So you can directly read the value and say, okay, if you fill up the water until here, it's like 50 turbidity units, 25, 15, 10, and so on. It's a really simple method to use. And this is the idea that we mount it close to the station. People can fill the water, just pour it off, and then it will be available for the next measurement. So the system is cheap. It's like, I don't know, 30, 40 US dollars per tube, something like this. You could do them by yourself. You also did this in Kenya, actually, where we modified them a little bit with a different color scheme, and then you can calibrate them. You have to calibrate them for the sediment loads, of course. Like if you're interested for like really sediments, then you take some samples, analyze it in the lab. To cross-check the turbidity, because this, of course, depends on every site.
Thanks. And the ones you buy from the UK, you also locally still recalibrate, or are they reasonably okay?
Yeah, for sediment loads, yes. For turbidity, it's actually, we assume it's okay. We have to check it actually when we're in the areas. And in Kenya, it was okay. Okay. It was the same tubes actually used. Yeah.
Good. Thanks for already picking up the tube while in the chat the questions were coming in. Katie, for you, a question about the nets, where you get them and what the net sizes are that you use. You didn't talk about this part so much, what you use them for, but I guess people are interested.
Yeah, for sure. So the nets are 500 micron mesh. I think the one in the picture probably wasn't, but yes, those are, we want to make sure we're capturing small enough bugs in the water. And I actually, the ones that are wood handled got a lot more expensive, like $100 more expensive. So this year I bought, they're probably made of aluminum this year, and I can still write on Sharpie on them, which is great. And I get them from like forestry suppliers or Fisher Scientific. Those are some of the companies that I can buy them from.
Good. Another question for you is whether you've explored the ideas or the idea of using an app so that people can down or upload the data directly.
Yeah, that would be my dream. And we're slowly starting to talk about this in the state of Wisconsin. we get a lot of our funding from the Wisconsin Department of Natural Resources, and they're a little bit limited. So it would be in partnership with them. And I think volunteers would love it. I think it would be a great way to engage with them and help them collect data, and then also confirm their, collecting, they're not getting ridiculously high numbers. We could use it for data quality checks like in the moment, which would be really cool, but we just don't have the capacity or funding to do it yet.
Mm-hmm. And you were mentioning the Department of Natural Resources. So there's a question about whether the data have been used. And then I add to that question, is it for the user a problem that maybe you get only the lower flow measurements? What do they use the data for?
Yeah, so because we're not getting peaks or things like that, we, the DNR biologists and such, the professionals, they're really using it for more of a screening tool to get understanding of the baseline nature of the streams. And then they will do, more rigorous watershed assessments. They might install a stream gauge in order to get more stream flow data. It's used probably more directly when we're collecting those nutrient samples and pairing stream flow with that, because that can be used for identifying impaired waters and listing those waters, which triggers a lot of things.
Mm-hmm. And related to that is a question on, do the volunteers get to choose where they measure? Do you have predefined sites? Is it random?
Yes. Yeah, volunteers do get to choose if they have a site they're passionate about, if it's, flowing through their property or in their local park, where they can do that. A lot of them want to monitor a site that is of value to a local effort. And so we will work with our DNR, Department of Natural Resources stream biologists, to identify sites that go well with the sites that the professionals are already monitoring. So it's kind of a blend, it's a conversation.
And maybe, Björn, the same for you. Obviously, you had to install these staff gauges, but did you predefine based on your modeling work or research where those locations are, or did you do this in collaboration with the community?
Partly. So the idea was actually in the beginning also that it will be taken up by the local water authorities in Kenya. So we had them as stakeholders mainly involved to also determine positions which are interesting. We also, of course, needed to take locations which are easily accessible. So it was commonly some bridges, or where people in Kenya, for example, go to wash their car. I mean, where really people are around. They go into the stream, park their car basically inside, wash it and put it out. And these are good places because it's frequently visited. So we did a kind of mix of all. And of course, one constraint was also we did it in a research area, which we were always studying before. So they had some kind of data to compare, for example, this radar data. So it was a bit a mixed approach. But also for some of these areas, we worked with the communities, and we had community meetings also to ask them where they might be interested. But it was a bit more the focus on the application side for the authorities to use it later.
Mm-hmm. And you showed some sites continue to have data throughout your entire sort of campaign or measurement period. Otherwise, people dropped off. Was that related to where you had these community events and where people were deciding on their location? Or?
Mm-hmm. Yeah, so the most active station, the one where we really constantly was very well covered with data, was the station in a community where we actually had a project since 2014 ongoing, where we did high frequency measurements. So the people knew us, we knew them a bit. We had community meetings with them, and they were kind of very engaged to also participate in this new project. And this was also actually the station where we compensated the text message costs. So on the system in Kenya, it's possible to transmit, it's kind of prepaid data, cards they use, and you can transmit the money back using the same cell phone system. So we automatically at the end of the month transmitted the costs basically back they had. And these were two things which were quite effective, knowing the community, but also compensating for the costs, which makes a lot of sense. So we are actually trying a long time to get a toll-free number, but it never worked out. So we had this kind of mixed approach.
Okay, cool. Going back to you, Katie, the 24% error correction factor across the state. The question is if you need to adjust for the stream bottom width, or do you know where that error mainly comes in? Is this partly of the roughness factor?
Yeah,
Or?
so this 24% correction came actually from Chris Stepanik's, I believe it's her PhD research in Wisconsin, and I have read it. I recall that, and if she's here, she can weigh in maybe. I recall that she did a comparison in many sites across Wisconsin and found this error consistently. So I don't think it needs to be adjusted for stream bottom width, but I can't be entirely sure.
Okay. And maybe, oh, there she is.
Yeah, I mean, I think I agree with what you just said. And in terms of the stream bottom width, it's just based on the entire process, the whole procedure. So basically, we just know that it overestimates by 24% based as compared to a Marshall-McBurney electromagnetic meter. And so in terms of the bottom, I think you mentioned the different bottom corrections, right? The smoother or rocky bottom. So it's all incorporated. I didn't separate it out.
Then our very first question was a more less project specific question maybe, but it's obviously interesting to hear your opinions on it. What do you personally or in your project consider the difference between crowdsourced data and citizen science? What's your take on it?
So
go ahead.
Yeah, I think this is actually a very good question, and we had we still have discussions about this, how to call it. If you check the literature, there's actually a huge amount of vocabulary for this, often used synonymously, so there's not really a difference. There's a very nice publication by Heckley, who defined 4 different levels of citizen science projects. And I like this definition actually quite a bit. So they say basically in the first level, it's kind of crowdsourcing. The words they then use are written like much because they call citizens as censors. So I would never call our volunteers censors, but it shows basically also like people collecting data. And this is what we also basically did in Kenya mainly. That's why I normally like to call from our Kenyan project about crowdsourcing. And then you have different levels. Like the next level would be some kind of citizens also interpret this data to a certain demand or amount. This is kind of, you often see it in physics, also the astrophysics, they kind of like interpret where the next star thing is going. A friend of mine is astrophysics, this is strange stuff, but so you can also interpret this data in a way. And then level 3 would be some kind of participatory science, which means that the citizens or community is also involved in the problem definition. So they define a problem and they also collect data then to solve this in a certain degree. And the 4th level, so-called, they call it extreme citizen science, would be that basically the community define the problem, they collect the data and they analyze the data by themselves. This is of course a level which is, from my point of view, very difficult to reach because I mean, it's basically completely done by the community. But it definitely makes sense to think about. And also what I picked up in the last year or 2 is also that, especially in the United States, is a discussion about citizen science itself, because often it's called participatory. It brings question, what is actually a citizen? So the question is really great because you see the amount I'm talking about, it's really, actually, it needs some proper definition and proper, you have to think it through. So,
Katie, do you want to add something?
Yeah, that's really interesting. And, you know, I think with WAVE, we're at that level too, where our volunteers are not defining the problem and whatnot. But it's also not crowdsourcing because I'd love to find ways for more volunteers across Wisconsin to contribute and participate without having to attend the training and get all this equipment, you know, just using what they have right there to participate. And so we don't have that easy access, which would be a wonderful way to engage people. But yeah, it's really great to think about the different kind of ways we can, you know, empower and include people in this process.
Maybe as a follow-up to Björn's question, who is a citizen in this case? And can you say something, because this is, I think, also a question that often comes up. on who was mainly participating, or who is mainly participating in your project. Björn, you showed that a few people make 80% of the measurements. Do you know anything about who they are? And Katie, for you, they go through training, so I assume you know who they are and how they found you, or how you find them. Can you both say something about that?
Partly we know, because we use this text message system. So we had the cell phone numbers, and also we did the survey among all users. So we really called them at a certain point together with the agency. But of course, not everyone was willing to answer. Also, like, I mean, SIM cards in Kenya change quickly. The phone number might be a different one. For the active ones is indeed normally some people, like either from the communities, which we had some contacts, or it's really some individual. We really see the need of collecting data to basically conserve their own environment they're living in. There's normally a very strong intrinsic motivation. And this is something which is, from my perspective, a bit different also from the cultural perspective. So like in Europe, or like in the global north, you might have different approaches, because people do this maybe more in their free time. They're interested or curious about science, while like in Kenya, it's really like people are concerned about their water sources. No, they're really highly dependent on it, and they try to contribute something to protect it further. And this is also something we have a bit like in this HYDROCROWD project, where we really have the different target groups. Because in Tanzania, if we work with tourists in Mount Kilimanjaro, to climb there, it's like $10,000. So it's definitely people from the global north coming there, and we are interested to see this difference a bit. But it definitely depends on the country, from my perspective, or from the background.
Very good point.
Yeah, that's really interesting. I would say in Wisconsin, it's generally people who, they do have to have the time to commit. So it's usually people who have the time, and then they're also already, really interested in natural resources, being out in nature. And at our trainings, we do generally target it to adults, but we have youth as young as 10, I would say, coming. And we have all the age groups, older than 10 represented. So we'll have parents coming, we'll have young professionals, people who are retired, kind of all ages. But yeah, we're definitely trying to improve access to our program to people who, aren't already engaged in their local nonprofit environmental organization, or people who don't already have easy access to the outdoors. So it's easy for us to fill up our capacity with people who come to us who already have access and interest. And so we're trying to do better to get to the people who have interest but may not have the access or the time.
Thank you. For everyone, if you still have questions, please put them in the Q&A. Katie, for you, a question as a European who has spent some time in the US as well. Considering that the citizens have a hard time with the decimal feet, what about using meters? Would that throw off the citizens completely, or?
I would have to experiment with that, because no one here thinks in meters, even though it's so easy. Oh, it's so easy. But yeah, I mean, even our professionals are doing it in feet. So I think that's why we tend to teach the volunteers what the professionals are doing.
Okay. Did you find, Björn, any part of the measurements that were more tricky than others?
So in general, I mean, kind of the easy parameters like water level gauges, which are kind of intuitive to use. So you look at the gauge, you read the water level, and you submit. This works well. If it's getting more complex, some kind of training might help. And this is, I'm really curious to see how it will work with the turbidity tubes, for example, in the field. So we will, of course, provide some explanation videos, or also some description next to the station, but it's a bit different than the approach in Kenya, where we had trained citizens. Or I mean, we met them, we briefed them how to use the tubes, and because yeah, I think the more complex the parameters get, it's more difficult also to really do it in the field. Yeah? I mean, also streamflow measurements is nothing you just do with some description on the paper. You really need to brief the people. Yeah? So yeah. And we saw also the data, I mean, like water levels were good, and then turbidities or nitrate is already more difficult and more complex to measure.
And for nitrate, you use the test strips, right?
Yeah, we use the test strips. I mean, there's another problem coming in this case because the water in Kenya doesn't have much nitrate because, I mean, the soils are deeply weathered and the strips are not available in the very low categories. I mean, it's like 1, 5, 10 milligrams per liter, something like this. So it was always on a lower border actually in this case. Yeah. But if you use more complex methods, like, I don't know, this kind of, how they're called in English, like you put this liquids, you measure the transmission. This is more expensive and you need to really clean it, you need to take care, and then the more complex it gets, the more difficult it might be, or you need to really highly trained citizens, but then, I mean, it's not really a citizens inclusive approach anymore.
Yeah. Thanks. We have one more question for you, Katie, asking about the Wisconsin flow measurements. What was the standard deviation or the ratio of the corrected volunteer results to the rigorous results?
Yeah, and I don't have that study in front of me, so I think it'd be great if we could share Chris's study with the audience after the fact.
We can put that in our living document, some links in there. The same was, there was a link question for the reference on where the correction factors come from. Maybe we can look that up there as well. So then there is, maybe this is for both of you, a question on checking out the gear to the participants. And if you assume that the non-consumable supplies, what happens to them? Do you request them back? Do most people stay long enough? Björn, did you have problems with the tubes disappearing? Both of you probably have something to say about this.
Yeah, for our program, kind of how it works is we partner with a local organization and we build their capacity to support volunteers. So in a way, when we give out our gear, we're kind of giving it to our partner to distribute to the volunteers. And when volunteers retire, which a lot of them do, a lot of them decide, you know, they get busy or they decide they want to do something else. They'll give it back to the partner, and we do have to resupply their chemicals for like their dissolved oxygen test kits, but generally, yeah, we're giving out new gear every year and we don't expect to give it back.
Yeah.
Actually, I cannot say too much about this because the only stuff we really give away are, in Kenya were the turbidity tubes and then this test strips. We didn't ask them back.
Yeah.
Honestly, I'm not even sure what happened to the tubes. So, I mean, during the project, they were available. It's a colleague of mine who's handling this in Kenya. I'm not sure if they actually, I don't think we asked them back now. Okay. So, and now on the HYDROCROWD, we won't, I mean, it's really like everything is available at the station itself, and let's see how long it will stay there, but actually I'm quite confident. So we didn't have much problems in Kenya with this either. I mean, sometimes some kids remove the signboards or so, yeah, this happens, but I mean, then we just reprinted them and put them back, so, yeah.
Thank you. Thank you both for these wonderful talks and for the Q&A and the discussion we had afterwards. Everyone in the audience, thank you for joining and asking these questions and being with us. You may wonder why we had a bit more time for the questions. It's because our pop-up speaker unfortunately couldn't make it. If you want to give a pop-up presentation, just a 2-minute presentation to highlight your own project, then don't hesitate to contact us. We're happy to have you in one of our upcoming weeks. And for everyone in Europe, next week we're back at 6 p.m. And in the US East Coast, we stay at noon. We look forward to seeing you then. Julia, do you have any last minute comments?
No, thanks so much, and we'll see you all next week. Thanks so much.
Thank you all. And Katie and Björn, many thanks for the nice presentations.
Thank you.
See you
Thanks.
next week.
Bye.